All right. I'm ready to get rolling. We're going to put some official meat and potatoes to what we did last week in the lab, looking at polyatomics, transition metals, and then we're going to move on to Lewis diagrams. Because of that, we're going to be doing a lot of drawing structures. One of your homework assignments is going to be drawing Lewis diagrams. The other homework assignment is that homework number 2 that I gave last week, but it wasn't due till this Friday. Okay. There's your joke for the day. This is a salt. Get it? Sodium chlorine, it's a salt.
Still don't get it.
Yeah, what does salt mean?
It's a salt.
Assault, like if you were to fight somebody or drag them or assault them or harass them.
Okay,
Oh.
Okay, polyatomic ions. Poly means many.
Gosh,
So polyatomic means many atoms. Okay. So when it comes to ionic and covalent bonds, as a reminder from last week, anytime you see IDE, all right, that typically means one element. ITE, ATE, and some other endings, this means you're going to have many elements involved. So what's that do for you? That means where you pull up the polyatomic list, right, and you're going to use that as reference. You don't need to memorize any of those polyatomics. You're welcome to, but that list will be always given to you. If at any point you forget your periodic table and or polyatomic list, I have my stack of periodic tables up here. One side's got the periodic table, the other side's got the polyatomic. Okay. That's it. All right. Polyatomics are usually going to have a metal and some non-metals, so that means they're going to be ionic. We got to look at the charges. So for example, if we have, let's do sodium, which is a +1 charge, and hydroxide, which is a -1 charge, we're going to do the same thing we did before. Ask yourselves the questions, are the charges equal and opposite? Yes, and so all they do is when they come together, they just cancel out. All right? Pretty similar to what we did last week. Is this a good refresher? Yes, they cry enthusiastically because they're ready for chemistry class. Okay, now's where you again. Cool, moving on. All right, we have, let's do another example. Let's do potassium bromate. 5 potassium on the periodic table. What's your charge, Alex, on potassium?
The charge would be +1.
+1, so K is +1. What about bromate? H means it's a polyatomic.
Oh.
Look at your list.
Oh, what? What am I
Find
doing?
bromate.
Oh, it's
Bromine.
it's bromine and oxygen 3.
So we got BrO3, and then what is the charge on that? That bromate. It shows you right here.
What?
Look, find bromate. BrO3. What's the charge it gives you?
Negative.
Negative charge. So this whole thing has a -1 charge. Okay. Yeah, Johnny.
Do you have another one of those charge papers that I could keep? That
Polyatomic?
that has the list of the.
Yeah, the polyatomic.
Yeah.
Yeah, the polyatomic.
You already lost yours again?
No, you gave me one, but I lost that first one.
You're notorious for losing stuff. Hit your head if it wasn't attacked. Alex, so those equal and opposite? Those charges? +1, -1?
What?
Are they equal and opposite?
Yes.
Yes, so that means they cancel out. So we just get K,
Oh,
B,
I understand now. Yeah.
RO3. So the formula for potassium bromate is KBrO3. Yeah, Morgan?
Can you go back to the last slide?
Real quick. Like that quick. Is this thing working today? Hey, look at that. We're working. Okay. So when it comes to your polyatomics, all right, the charge is given, what it is given, all you got to do, and here's the big thing. People get stuck. All right. Am I good to move on? Okay. People see bromate, and they blow right past that ending, that ATE ending. This means it's a polyatomic. It is not bromide. Bromide would just be Br. And then, well, that looks ugly. Bromide would just be Br, and then you look at the charge. You find that is a -1. This is bromide. This thing is really laggy today. Bromate is BrO3. Good here? Yeah, what's up, Hutch?
If we kept the brackets, would he count it wrong, or would it not matter?
Well, if you were to write this out or type it out, yes. Sorry. It would be okay. Like if you were to put this, KBrO3. That is technically the same thing, but remember, scientists love to be lazy. If you don't need it, drop it. So let's look at potassium manganate. This one we're going to have to keep the brackets in, at least I believe so. Manganate. There we go. Yep, we're going to keep that. Let's do a different color. Charge of potassium is still +1. What's manganate? Here, guys. What is Lil? MnO42. It's going to be a fantastic day because Lily is participating today. Legit makes me super happy. What's the charge on MnO42? -2? Oop. Yep. Are those equal and opposite, Lil? You got +1, you got -2? Well, they're opposites, but are they going to cancel out? No. So you got to do a little crisscross thing. This 2 is going to go to the K. And then, oh, I lied to you. We're not going to need the brackets. MnO4. Yeah.
Would you need the brackets if, say, potassium was something like calcium?
Yeah, so if we did, not calcium, let's do real quick, let's do like calcium and hydroxide. -1, this is +2. So when you crisscross them, that 2 goes on the outside. Okay. If you don't need the brackets, you can just drop them, forget them. If you do need the brackets, okay, keep it in, 2 there. Cool? Any questions? All right. Now let's go from the formula, and then let's go to the name. Now I'm willing to bet somebody's going to appreciate this last one. Let's do number 4 first. All right. You have the metal, which is what? What's the metal in there?
Is it potassium?
Absolutely, you got potassium.
And that's nitrate, isn't it?
Potassium, and then we're going to find NO3 on the back of this periodic table list.
Nitrate.
Nitrate. All right, there's nitrate, and then there's another one, isn't there? Nitrite. Okay, you got to be careful when you're paying attention. Nitrite would be NO2. This is NO3, so it's nitrate. So be careful when you type in your answers in the homework. Spelling does count. Last one. What's going to be, Evan? Some candy.
Well, you got sodium,
Sodium.
and
What's the
then
other one?
CH. Let me look for it. C2H3. Acetate, yes.
Close.
Acetate.
Acetate. Fantastic. All right.
Acetate.
That's all right. We're finding new words we've never seen before. So we do. Na is sodium. And then this C2H3O2, we look on our on our polyatomic list, and it is acetate.
And that's number 5.
That's number 5 right there, that last one. Yeah, what's up, Hudson?
Is acetone just acetate minus the oxygen?
Acetone? No. I don't believe so.
Alright.
I'd have to look at that real quick though. I think they're similar. I'll have to back on that. I'm pretty sure not. I digress. Before I say something that's wrong, acetone. Nope, that's toluene. I don't remember.
Alright.
Now, Johnny, what's that spell?
What is what spell?
N-A-C-H-O.
Nacho.
Nacho. You know what's really funny?
What?
One of the ingredients in nacho cheese is sodium acetate. So in nacho cheese, you'll find nacho, which is sodium acetate. It's a preservative. Usually on a lot of things that have a very long shelf life or really heavily processed foods will have some sort of preservative in them. One solid preservative is sodium acetate. So you should be able to now, I'm willing to bet if you look on some ingredients list on some things at home or some sodas you drink, that you'll be able to read some of the compounds that are within your drink. So is there any in there, Brian, that you can read now?
No.
No?
Handle those and I don't know, something acid.
Yeah, we haven't learned about acid yet.
Nacho fofo.
We have, oh, your ingredients on the right here.
Oh. You know what?
Potassium benzoate,
That's potassium.
potassium and
Benzoate.
benzoate. Wow, that's crazy.
Oh yeah, it's right there. C7H5O2.
Zero
Yeah,
fofo.
C7H5.
There's probably another one here. 2 or 3 in there. You can probably read now.
Read them.
Would you understand them fully? No. But you understand a little bit more? Maybe so. Okay. All right. We got on polyatomics. Using your list to name them. Make sure you pay attention to charges. Let's now do transition metals. We did this in our lab last week, but now let's put some nuts and bolts and a little bit of explanation to it. When you have a transition metal, so somewhere in the middle on our periodic table, here, kind of to here. If you have any elements kind of in that middle block, for reasons we don't quite understand yet, but these metals can particularly have different charges within them. So iron, for example, could be iron 2, iron 3, or iron 4 on the charge. Since they can be different ones, we have to indicate it with just some Roman numerals. And it's pretty simple from there. All right? And since it's metal to non-metal, it's still ionic, meaning no prefixes. All you got to do is include what you got. So for example, if we have Fe2O3, we got to break this down a little bit and do some reverse engineering. So let's break it into its separate parts. Fe and O. Johnny, help me out. What's the charge on oxygen?
-2.
-2, absolutely. We're going to do the reverse crisscross method. So the 2 that we brought here, this 3, we're going to bring here. So iron gets a +3 charge. So you follow me there? Right, John?
Yeah.
And what would we name this? Well, Fe is iron. iron is a transition metal, we include parentheses of what the charge is. So this iron becomes iron 3. Instead of oxygen, what's the ending going to be there? Johnny?
Oxide?
Oxide, that's it. Do you know what iron oxide is?
No.
Yeah, you do.
Rust.
If I leave my bicycle outside, what's it going to do? It's going to rust.
Rust.
Why is that? It's because the iron chemically bonds with the oxygen and makes rust. One of the things you made last week was an iron compound. And what do those colors look like? They were the browns and the oranges.
Rust.
You were making something similar to rust, but it wasn't quite rust. What about, oh, let's try that again. Let's use a different color. What about another form of rust? Just FeO. What's that gonna give us? Mark, what do you
Iron
think?
oxygen.
Iron oxide. I'll give you that. But iron what oxide?
Iron 1.
What's that? If it's a covalent bond, we include prefix. This is ionic because it's a metal and a non-metal. We got to figure out what charge of iron we have. You ready there? So let's rip it apart. Let's rip the iron away from the oxygen. What's the charge in oxygen? It's on the board. -2. So, would you agree with me that these charges are going to cancel out since it's just Fe and O? It's a one-to-one relationship. So what does iron have to be then to cancel it out? Absolutely, it's got to be a +2. So we name this as iron 2 oxide. Yeah.
Isn't another way to say something rusted like it oxidized or something?
Yes. Oxidation is a type of chemical reaction we haven't talked about yet.
Is that why?
It's the same reaction type of things burning, you breathing, anything being relatively introduced to oxygen is oxidation reaction. Yeah,
Why does it take so long?
that's reaction rates. So reaction rates are based upon their environment. Kind of thinking about Kool-Aid, mix Kool-Aid with cold water. You gotta stir that bad boy for a long time. But if you change the environment, if you use hot water instead, that water dissolves super quick. So reaction rates are based upon what the environment looks like. So if I go throw a hunk of iron outside on the sidewalk, it won't rust very quickly. However, if I throw a hunk of iron next to a pond, since there's water there, there's a whole lot more moisture in the environment that speeds up the reaction.
How does that work? How does it speed it up?
It's called a catalyst. Catalyst allows chemical reactions to speed up, but not be part of the system.
Like, how does it speed it up?
It's like moisture raises humidity.
I would say a good analogy would be if we had a big old pile of rocks we needed to move 100 feet. You don't get anything. You just gotta carry the big old pile of rocks 100 feet, one by one. Me, on the other hand, I get a nice truck and I can just throw them all in and drive them over. Is the truck part of the chemical reaction? Kind of, but it is not being changed. The truck just goes back and forth. So catalysts allow the reaction to happen more quickly by kind of being a vessel for it. Does that make sense?
Kind of.
When you go into biology, have you taken biology yet?
Yeah.
Okay. Did you talk about enzymes?
Yeah.
Enzymes are catalysts. They hook onto proteins and they allow it to be happening more quickly. Are enzymes used? No, but they're part of it. In Chem 2, you look at reaction rates a whole lot more. There's a bunch of math in there that I just don't talk about in Chem 1. Good question though. Okay. Alright, great background, alright. We're gonna switch gears a little bit. Instead of compounds, compound naming, let's switch gears a little bit and let's think about electrons. We're now we've got not only compound and compound naming down, we're now gonna start drawing compounds. And what do they form? Where are the bonds at? How do we move forward from here? So when we look at the periodic table, we should be able to uniformly agree. Everything in the first column has one valence electron. Everything on the one from the halogens, the one from the noble gases, have 7 valence electrons. Let's look at a little more closely what those electrons are doing. So everything that's kind of right here, I'm going to go through with these examples right here. So this is kind of like my short and sweet. All right, how do we draw our Lewis diagrams and Lewis symbols a little bit quicker? So the first thing we do is we look at carbon, for example. We find an element, we look at how many valence electrons it has. Caden, how many valence electrons does carbon have? 4, fantastic. Ready? All right. As we fill in those valence electrons, what's the charge on an electron, Caden?
What?
What's the charge on an electron? You're killing me, dude. You're killing me. This is like week 2, week 3 of stuff. Brian, what's the charge on an electron?
Plus or minus 4.
What's
I
the
got it.
charge of an electron? Johnny,
Positive.
No.
what's the charge
Negative,
of an
negative,
electron?
negative, negative, negative.
Negative.
Oh my god, you bro.
I took to be a little.
If I have an aneurysm and die because of this, I just want you to know you can blame it on all of them. All right. When the ambulance comes rolling in here and be like, what happened to him? That was that. Okay. Electrons are negative. All right.
I thought it was positive.
It's protons.
Yeah, I know, I mixed it up.
It's all right. Put you on the spot and you. Okay. Electrons are negative, which means they want to spread out as far as possible. When you are looking at your diagrams, we're going to fill in the electrons, but make them as far as possible. So carbon has 4 valence electrons, thanks to Caden. So I'm going to put 1 on the right side. Then we're going to fill in our electrons, but they're going to be evenly spaced. 1 on each side. Follow me there? Electrons are evenly spaced apart. What happens if we had something that had a different number? Kind of like fluorine. How many valence electrons fluorine got? 7. Fantastic, Brian. We're going to fill in the electrons here again. We've got 1, 2, 3, 4. Now we've filled in all of our 4 orbitals once, or suborbitals once. We're going to fill them in again now. So now these electrons have pairs. 2, 3, and now we have 7. Okay. What's your question, Johnny?
Never mind.
Okay.
Never mind.
Stay in your lane.
Yeah.
Hey, I don't need help. I'll roast both of you. Okay. When you are drawing your Lewis structures, the only thing you really need to be in consideration of is what are the valence electrons doing? So 1, 2, and 3. All right, 1 on each side. Here's an example of a bad Lewis diagram. Would be 1, 2, and 3. Okay. All right. When you're drawing them, you got up, down, left, and right. You don't want them to have them equal spaced. All right. You want to fill in 1 on each side first, and then go back and fill them up again. All right. This will make sense here in a little bit when we start doing bonds, what bonds look like. But for now, we're just going to go for here. Good there, Lauren? What's charge an electron? I thought you were going to be with me here a second. All right. Let's now move this to the next step. If we look at elements and their valence electrons, we can predict what their Lewis structures are going to look like. For ionic ones, I really don't like them. They're not super helpful. We're still going to do them. We're going to do this a whole lot more with covalent ones, and we'll see when we get there why that is. So let's look at lithium and fluorine, for example. Lithium and fluorine. All right, Lauren. How many valence electrons does lithium have?
1.
1, fantastic. And how many valence electrons does fluorine have?
7.
7, absolutely. So we're going to do 1, 2, 3, 4, 5, 6, 7. We good there? Okay. In an ionic bond, I give you a hint at the top. Evan, you okay?
I'm very tired.
You need to do some jumping jacks, and do some push-ups?
Yes.
Want to stand
Yeah.
up?
Yes.
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 Push up contact.
Do you want to do them? You're good. If you
No,
want to
I-
wake up, just do a little.
Yeah, I'm tired.
No.
Yeah, John.
I'm tired.
Okay. In an ionic bond, I give you a hint at the top, Evan. Are electrons taken or are they shared?
In ionic bonds?
Yep.
No, they're not shared.
Which means they're what?
Taken.
They're taken or they're given. So this electron right here is going to go to this empty spot right here. You see that, Evan?
Yes, I can see that.
When lithium loses an electron, what's the charge on it?
Just regular. 0.
Lithium loses an electron?
It's 0.
Try again.
Ooh.
Kick an electron out. What's the charge?
Oh, plus 1.
There we go. So lithium plus. Fluorine gains an electron.
Minus.
So it has a negative charge. We're going to draw in all of those electrons. So when you draw a Lewis diagram, make sure you include where those electrons are at. We good here? I can't stand this chair. There was a joke in there, Kate. Yeah. Do you live out by the airport?
No.
Because these jokes are just flying over your head all day.
Sodium.
I know, I'm sodium funny, all right? Hudson, you ready? How many valence electrons sodium have?
1.
1. How many valence electrons chlorine have?
7.
7. 1, 2, 3, 4, 5, 6, 7. Follow me there?
Yeah.
Same thing as the other one. This electron is going to go to the empty spot right here. And what's that going to give us in the long run? That's going to be sodium with no valence electrons,
Plus 1.
plus charge. And then chlorine with a full octet and has a negative charge. We good there? So when you're drawing Lewis diagrams for ionics, this is what it's going to look like. Okay. Covalents are a whole lot more helpful because we're actually going to draw some bonds. This is technically a bond, but it's not a very good one. So now let's do this for covalent. And we're looking great on time. Do you want to do one more example? We're going to move on.
No.
Okay.
1.
Brian, you want to do it?
Yeah.
No.
You can.
No. Maybe you should.
Okay, move on. Okay. When you are doing covalent ones, though, covalent bonds, since they share electrons, they might share one of them, which is a single bond. They might share more than one, 4 electrons, which is a double, or you can even in some cases get a triple bond. Okay. We're going to see when those single, double, or triple bonds form by looking at the valence electrons. So everything that's in this page right here, which is on Schoology and everything else, we are going to look at with these couple of example problems. All right. Well, did you get candy yet today?
Nope.
You got a piece of chocolate. You interested in that?
Sure.
It's Baby Ruth.
I'll have to save it.
You have to save it?
Can't eat at the moment.
Can't eat? I'm sorry. All right. Help me out. How many valence electrons does carbon have? Actually, let's take a step back. Carbon, tetrafluoride. Carbon C, Do you have the prefixes in front of you? Remember what the prefix 4 means from last week's notes? Tetra.
Tetra is
But
3.
my other notes.
Tri is 3. Tetra is 4. So, are you good with me that this is CF4, carbon tetrafluoride? Okay. Let's find the total number of valence electrons. What is going on? Let's find the total number of valence electrons in CF4. We have carbon. How many valence electrons are in carbon?
Isn't it -4?
It's just 4. Not the charge, just how many valence electrons. So carbon has 4 valence electrons. Fluorine has how many? The way right hand side. Should have a 7 at the top.
Oh, yeah, 7.
Okay. We have 7 valence electrons, but we have 4 of them. So we're not going to count just 7.
It's gonna be 28.
We're going to do 4 times 7. So it's going to be 28 valence electrons. You get there, Lil? 4 times 7, 28. So how many do I have in total? 32 valence electrons. We good there? When I draw my diagram, we are going to have all 32 of these valence electrons accounted for. So if we think about carbon tetrafluoride, the central atom, what's going to be in the center of everything, is going to be carbon. It doesn't make sense fluorine's going to be in the middle because there's 4 of them. You can't have 4 things in the middle. Carbon's going to be attached to these 4 fluorine atoms. Is everybody good there? We're going to assume that it's a single bond. If we put all of our electrons in and we're either overcounting or undercounting, we're going to change those bonds around. But let's look at fluorine. Fluorine wants to have how many valence electrons to make it happy? Evan? What's the octet rule?
8.
8. There are already 2 electrons accounted for in this bond. So how many more do I need then? If I want 8, but there's 2 accounted for. 6. Look at this. That fluorine now has a full 8.
Where'd you get the 2 from?
2 from the bond.
Does every bond have 2?
Every bond has 2.
Oh.
But we don't have to draw the dots, right, for bonds?
Yeah, when you do a bond, you do a straight line. The lone electron pairs stay like that. So, for every bond you have 2 electrons. All right, Evan, count how many electrons are accounted for in that picture.
Well, so there's 8 for the bonds, right?
There's 8 for the bonds, yeah. 2, 4, 6, 8, absolutely.
8, and then 24, so 24 plus 8 is 32.
32. So let's see how we did that. There's a couple different ways you can count them. I'd recommend counting everything in that group and see how there's 4 of those groups. So Evan, help with me. We got 2, 4, 6, 8 right here, right?
Yeah.
8 electrons. What's 8 times 4? 32.
32.
All 32 of our valence electrons are accounted for when we draw what's in red right there. That is the Lewis diagram for CF4. Okay. I'm going to stay there for a hot second. Try silicon out for me. Look at silicon on the periodic table. Look at oxygen. See how many valence electrons you're going to have. And let's see what we get.
silicone S4. Wait, no, I read that wrong. Never mind. Yeah, no, that's right.
Mm-hmm. Sounds right.
And there's two, and oxygen has 6.
Yeah.
And there's 2 of them.
So
So,
why there?
yeah, 12.
So we got silicon dioxide, right?
Needs to be 16 in tow.
So we got Si is 4, silicon's 4 valence electrons, oxygen is 6, there's 2 of them, so you got 12 in total. So let's draw this out. Let's try to draw it out at least. We
Where'd
got-
you get the 20?
That's 2 oxygens.
Oh, okay. Oh, yeah.
So we got silicon is going to be in the middle, because it makes sense. It's not going to be silicon on the outside, oxygen, oxygen. We'll do one bond in the middle, and then let's draw our oxygens. How many electrons does oxygen want?
It wants 8.
Wants a full 8, so let's do this. Let's add 2. Let's add a full 8
Yes.
everywhere. What problem am I going to run into, though?
Oh, silicone. Does it need,
Silicon? Absolutely. Let's put.
but then you have too many.
We have too many. How many do I have right now?
You have 20,
I have 20. How many do I want?
16.
16. If we have too many electrons, that means we're not sharing enough. We need to share some more. So what do we do here? We take 2 electrons away from the bottom for both silicon and oxygen, and we make this a double bond. How many do I have now?
16.
Close.
18.
18.
Yeah.
So I got 2, 4, 6, 8, 10, 12, 14, 16, 18. We have 18 electrons drawn on our picture. We want 16, which means I'm going to take some away. We're going to take some away from silicon. We're going to add in another double bond. And so let's check this out. How many electrons do I have now? 2, 4, 6, 8, 10, 12, 14, 16. Every valence electron is accounted for. So silicon dioxide, there's 2 double bonds to the oxygens on the outside. When you're drawing these, you want to double check yourself before you wreck yourself. Everything wants 8, right, Evan?
Yes.
Does oxygen have 8 electrons on it?
Sure. Oh, no, not right.
If I cover up the silicon, can you see the 2 double bonds there?
Yeah, and those are 2 each, so it does.
2, 4, 6, 8. Does this oxygen on the left side have 8 electrons?
Yes.
Yes. Johnny, you ready? Does the oxygen on the right side have 8 electrons?
No.
Well, we got 2 here,
Oh, yeah.
2 for
yeah.
each bond, so 2, 4, 6, 8.
Yeah.
See that on the right side? Hudson, you ready? Silicon in the middle. Does it have 8 electrons? 2, 4,
yeah.
6, 8. Everybody has 8. Everybody's happy. Okay. So when you're drawing covalent compounds, you can now predict, all right, where those bonds are going to be for some simple ones. Maybe we'll get crazy with it and do some crazy ones, but for right now, we're gonna do one more and we'll call it done.
Done.
Want to call it done? You sure you don't want to do it for water? Dihydrogen monoxide?
Sure.
Sure.
It's
okay.
just H, one bond, single bond, single bond, O.
And,
Vote for more
all right,
guys.
we'll leave that for tomorrow. Okay.